Hi there, I'm Mr. Sand, and we're going to talk about Unit 4 now. This is now the periodic table. We're moving along through all the units here in chemistry, and today I'm going to talk to you about filling up electrons. We're going to spend some time on this. When I say fill up electrons, what I'm really getting at is something called electron configuration. You see, every atom in the periodic table has a certain number of protons. And if you go up to a larger atom, that just means that they have a different number of protons. It means they have a larger number of protons. If you go down, that means they have less numbers of protons. The simplest atom you can make is hydrogen, and you can see that one right in front of you right now. It's a representation of it. And since we're not going to be going through any of these kind of like wave models of the atom, we're just going to be sticking with the Bohr model of the atom. There's a sort of a workaround that I'm going to tell you about today, and this workaround will get you through all of general chemistry just fine, unless you're working with the wave model of the atom with the SPDFs. If you have anything like that in your future, then you're going to need to learn about that. But in this class, and for just general chemistry, you don't need to know about that. You can use everything that I teach you and be absolutely fine and do very, very well in general chemistry. So, we're going to just stick to the easiest way of going through chemistry here because there's no need to complicate things. So, let's try it. So, just to start off with, I'm just going to review what the Bohr model of the atom is. So, you see this in the middle here, you've got this red thing and you've got this blue thing orbiting around it. In this representation, it just looks like a red ball and a blue ball orbiting around. Now, in the Bohr model of the atom, that doesn't necessarily have to move around like that. It can just be a stationary point and you'd be fine. In fact, this orbiting right here seems a little weird to me. But let's just keep on going with this little simulation. This is a great model here. I love this slide. It shows that an electron can take up different positions in an atom. This whole thing right here are the potential shells of an atom. The closer you are, the lower energy the electron has. So there's the first energy level, which seems really close to the nucleus to me. This is not to scale. And then you get further and further out. These shells go higher in energy. So these are called energy shells. They're just called shells, if you like. And we can number them 1, 2, 3, 4, 5, 6, out to infinity if you want to. Now, the important thing about this Bohr model of the atom is that if this electron absorbs energy, it teleports up to the next energy level. And if it loses energy, means it gives off energy, then it goes down to an energy level below it. Now, if the atom's behaving like it normally behaves, the atom is going to fill in these electrons, or whatever number of electrons it has, in the inner shells first before it fills out the electrons in the outer shells. The reason being is that the higher these electrons are, the higher energy they have, the less stable they are. So the electron's going to pack the electron. The atom is going to pack the electrons in the most stable configuration as possible. Now you might think, okay, great. If an atom needs to pack, I don't know, let's say like 22 electrons around it, then it can just pack those 22 electrons in that first shell. Well, that's where some rules come in, and we're going to go through some of those rules today. But I just want to, again, show you that if you have electrons around here, they go up with the higher energy. Okay, let's see what else we can talk about. Oh, there we go. There's a little energy going in, and energy in the electron going up to different energy shells. I hope they have a one where they come back down. Here we go. There it is. That's good. So if it falls off, if it goes from the higher to a lower, it often emits a photon, which is energy that we see as light. And every atom has a different sort of fingerprint in terms of the electrons jumping from certain levels to other certain levels. It's all to do with stability. Now, this proton right here is just one proton. That's just one electron. This is simple for hydrogen. The Bohr model doesn't really work for a larger atom, larger than hydrogen. but we're going to pretend that it does because it works for us. This model works for us. Let's say that you have, I don't know, 3 protons, and then you probably would have 3 neutrons as well, or 4 neutrons if you've got lithium. For those 3 protons, if this element were to be neutral, it would have 3 electrons. And there's a certain way that those electrons are packed into this kind of these empty shells here. And that's the subject of today. So let me start with that. So there is a rule. There's a rule in which electrons store their electrons, when atoms store their electrons around them. And that rule, I call it a filling up rule. So I'm just right. There is a rule. There is a rule. For how for electrons in atoms. For electrons in atoms. Okay? It's a filling up rule. There is a filling up rule. I'll say filling up rule. And that rule, that filling up rule, is called something very specific. It's called the Aufbauprinzip. Yeah! It's the Aufbau principle. For those of you who speak German, you know that Aufbau just means filling up. So it's the filling up principle. I didn't really give you any extra information because I say there's a filling up rule. It's called the filling up principle. Okay, great. But if you look this up online, they're going to start telling you about things like 1s, 2s, 3, 2p, and so forth. And you're going to see arrows going like not like that, but like this. It's the same principle that I'm going to show you with these little Aufbau boxes. I'm going to tell you this in a bit. The Aufbau principle is the same principle that I'm going to show you right here, but I just use boxes. It's easier for me to visualize this without introducing you to the 1s, 2s, 2p, 3s, all that weird stuff. Right. So in an atom, let's use like boron for an example. Boron's a good example. I'll use a different color for boron. For boron, how does boron fill up its electrons around itself? So boron has how many electrons when it's stable? To answer the question, you need to know how many protons it has. So it has 5 protons. So let's say it has 1, 2, 3, 4, 5 protons. Great. And it's going to have neutrons too, but we won't draw those in. Now, it's going to have 5 electrons as well. I'm going to just show you what this is going to look like. So you've got this first shell, and then you've got another shell. That's all we're going to need for boron. And I'm going to draw the electrons into here. Here we go. So here's an electron. Boop. That's an electron. I'll draw another electron. Boop. Right there. Those are the first 2 electrons. Now I'm going to go up here. That's an electron. That's an electron. And that's an electron. So I put 2 in the first shell and 3 in the second. So I'm going to call the configuration for boron, we write it like this, an electron configuration for boron. We have a special way of writing it. For boron is this. B colon 2 dash 3. That 2 means there are 2 electrons in the first shell, 2 electrons in first shell, and there are 3 electrons in the second shell. Oh, that's pretty easy, Mr. Sand. Yeah, but how did you know that there were only 2 in the first shell? And we could put the rest of them in the third shell. You didn't know that. If you said you knew that, you're lying. Here's how you know. It's this thing I'm going to call the Aufbau boxes. And here we go. I'm going to give you some examples like this. Yes, I want to